Struggling with slow simulation and poor mesh quality in your FEM solver? Let me show you how remeshing can boost speed and accuracy in just a few steps. Let's dive in. One of the major challenges in FEM simulations is mesh quality. As the material deforms, our mesh can become distorted or inefficient, leading to inaccurate results or computational inefficiencies. This is where remeshing comes in. Omega H is an ideal choice for remeshing because of its scalability and performance. It is designed to work efficiently in parallel on both CPU and GPU systems. This makes it perfect for large-scale simulation that requires dynamic mesh adaptation. The library offers advanced algorithms for mesh refinement, such as coarsening and refinement based on solution gradients, which ensures that the mesh adapts intelligently to the problem. Plus, it is highly flexible and integrates well with various solver architectures. For my solver, integrating Omega H allows me to combine efficient remeshing with the power of GPU or CPU acceleration. Here we have our own class remesher, which performs the remesh and the results mapping in the function write domain. Inside the constructor, in the function adapt with thresholds, we can force our element size limits on the Omega H remeshing options, or we can also set metrics in different ways. We go also in an element loop to check size and edge angles in the same code. In this case, we uncomment these limits in order to refine our mesh and compile the program. This later will be a solver parameter. We run our classic compression example and we open the results using ParaView. We can see at the left our original mesh with about 2000 tetras at the left, whereas our new mesh is about 10,000 elements at the right. Now we do the same but for a larger period of simulation time in order to evaluate the importance of remeshing. We run about 20 times the previous process time and we can see that our first mesh in which we plot plastic strains is severely deformed. At right, we open our new refined mesh and we can see several parameters as element quality and element length. Also, I have saved with Omega H the mesh before being changed, and we can see that from this file we can check several parameters as size, metrics, density and pointwise, which can be all used as remeshing parameters. Here we are mapping a nodal field from the old mesh to the new generated mesh. For this, I am searching from all new mesh nodes in which old element falls and interpolate between its vertices. We are using an excellent feature from Omega H, which is a parallel loop that will be run in parallel using either CPU or GPU architecture. Here we are writing the B field, which is the interpolated field, and printing the element connectivity. Also, since I have observed some noise in the interpolated fields, as you can see in the plots, I added a previous control, which I'm showing here, in which I check distance between the new nodes and old nodes. And if this is below a certain threshold, I directly equals the new nodal field to the old. After this correction, the results are quite smooth. As you can see here, I make an inner loop from the old mesh nodes and search for a distance. Here you can see the correct field, which is a lot smoother. Finally, you can see how is a remeshing and remapping of the entire domain after a considerable time, taking as a remesh criteria a max and a min element length, directly from the options. You can see from both clipping planes that the mesh at the right is much smoother and the mapping is correct. But wait, what if instead of remeshing by imposing an element length, you want to refine locally based on a metric? As for example, mesh element angles beyond certain limits. Keep in touch and I will show you how to set this and also how to perform successive remeshes in the following video.